by Professor Roberto Cid Fernandes. Just to introduce, these are the 10 galaxies that we have studied, and the proposal was having a little of everything like ellipticals, spirals, and interaction galaxies. Then I treated the data like data cubes, as shown in this illustration. Then the first thing that we do is masking the data, because we need to constrain the analysis just to the galaxy. Then I get the cube already with the stars masked by Fabio and Luna, like this image. Then I add one more mask that makes a contour around the galaxy. I will not explain how I did this, nor other things, because of the time, but all the details are in my dissertation. Then the main goal with these masks is to define the best useful area of the galaxy. Then this step is very important because it will influence our results. Besides providing a big reduction of processing time and storage, here, for example, we have a reduction of almost 2 billion pixels. Right. Then after the mask, we apply two methods, the PCA tomograph and the all-star spectral fitting. First, I will show some results of PCA tomograph, which changes the coordinates of the system by the variance. Then we get a new system, and this new system have the tomograms, which are images formed by combinations of the flux in each filter, and these combinations are given by the eigenspectrum. Like this plot, where here in the x-axis we have the 12 filters, and the y-axis we have the eigenspectrum. Then we make different configurations of PCA, and these configurations are basically applying mathematical operations in the original data. Then here we can see several tomograms with different structures, but the problem is interpreting the eigenspectrum is really complicated, like this one, but unfortunately this happens for the most of the tomograms. But a few cases are easier, like this. For the PCA normalized by the filter R for the same galaxy, where we have this tomogram 8, where we have this darker region, and looking the eigenspectrum 8, we can see that the responsible for this region is this filter that contains 8 alpha, indicating that this is a region of star formation. Then here we have other tomograms for the galaxy NGC 1326, and we can see several rings. And here in the tomogram 7, we can see this darker structure, similar a spiral arm that we can't see in the original data. But when we comparing with the Hubble image, we can see that this structure is a region of dust. We also can use the PCA for amplify some signal, like we did here, where we amplify the signal of the ring by the sum of the tomograms that show the ring. Then, despite the interpretation of the eigenspectrum being really hard, We also can use other tools for helping us to understand them, like using the code star. Then here, for example, we have the stomogram line is very similar to the map of the dust optical depth from All-Star. And the idea here would be make a reverse engineer. Then we also did RGB compositions of the tomograms that, besides being beautiful, they are spatially cohesive, indicating that they have a physical meaning. Then that's it. Now I will show some feeds and maps from All-Star. Then the All-Star is a code of spectral synthesis whose idea is that one galaxy or region of it is formed by various stellar populations with different ages and different metallicities, such that the observed is a sum of these components. Then here, in this plot, we have the All-Star's stellar base with 16 ages starting in 0 until the 14 giga-years, and 5 metallicities starting 0.2 solar metallicities until 30.5 solar metallicities, a total of 8 stellar population. And here we have the emission line base, which has 9 components with these 5 line groups. And each one of these 9 components is one of these stars in the BPT diagram. And these gray points are random combinations of these 9 elements of the base. Then we can see that this base has a realistic pattern. Now I will show some feats from All-Star for the galaxy NGC 986. Then here we have 3 different regions: the center, the middle, and the spiral arm. Here in the x-axis we have the wavelength, and in the y-axis we have the flux. The black points are the observed data, and the red dashed is the field from All-Star, which is a little hard to see because the data and the model are very close. And the pink one in the background is just this. Here we have the model from All-Star for the 12 filters, and here the original flux. And we can see again that they are very close, with lower ratios just in the bluest filters. Right. Here we have a test of photometric errors, where the purple histograms are the observed data minus the model divided by the error. Then, if they were perfect, they should be like this black dashed Gaussian with mean 0 and standard deviation 1. Then we can see that the error is overrated by about 2. And this happens for all the galaxies, not just for this one. Now I will show some maps and radio profiles for the galaxy NGC 986. Then here we have a map of the stellar mass surface density, and here the radio profile, where the x-axis is the distance from the center, and these red dashed lines are 5 and 10 kiloparsecs respectively. Then here we can see that the stellar mass decreases towards the edge as expected. Here we have the map of the average of the age log weighted by the light, and here the radial profile, where we can see that this galaxy have a star formation here in the center, and outer population here in the bush becomes younger towards the X. Here we have three maps for the galaxy NGC 1365. Then this first is the observed luminosity at the G-band, and the third is the map of dusty optical depth from our star. Then here in the middle we have how this galaxy would be seen without the dust. Then we can see visually that looks consistent. Right, then we also did RGB of 8, where the red is the world population, the green intermediary, and the blue the young population. Then here in the first line with dust, we have that the maps looking good, but in the second line without dust, we have a problem with the regions of low surface brightness here in blue, and this is a problem that we are working in. Then I did all this plot and a few more for the 10 galaxies, and all they are in my dissertation available at this link. Finally, the conclusions. First, we need to improve the preprocessing, especially in regions with low surface brightness. And with PCA, we have that the tomograms indicate a good potential, but the interpretation of the eigenspectra needs further work. And with All-Star, we got great spectral fits, maps, and consistent radial profiles for various properties. Then this is a promising study to be applied to other S+ galaxies. Then that's it. Thank you all for listening.
Thank you, Julia. Really nice and heavy and complete work. Here is Catalina. Want to ask? Go ahead, Catalina.
Hi.
Catalina, sorry.
It's everybody here. Hi, Julia.
Sorry.
Hi.
Yeah, very nice talk, Julia. I have a question about the masks.
Yeah.
Is that an automated process? Because I saw that it follows really close the morphology of the galaxy. And if this is automated or not, which filter did you use to choose the mask?
For make this mask here,
I can't see your screen, but we can see the screen, but not the presentation. But the mask of the galaxy, you have the mask of the stars. You mask out the stars, and then you have a mask that only selects the galaxy. And is that automated, or how did you do that?
the stars who masked is the Fabio, and the other mask that I add is I use a filter of ND image that makes a median of the how can I say this? I use the mask of the Fabio, then I make it's like a really contour in the galaxy that I use this filter that makes a median, where because if I don't this, I did holes in the galaxies. Then this way I make a smooth contouring.
Oh, okay.
I don't know if I can explain this.
But did you? My question is, did you choose the contour by hand, or is it automated?
I choose the parents for each galaxy. Then I make for same.
Okay, thank you. We have other questions here, but I think Denise
Yes,
raised.
yes, Denise is raising the hand. Go ahead, Denise.
Oh, hi. As you see, as I cannot be there at the beach with the others, I pretend I am anyway. Nice talk, Julia. My question is, I don't know if I got it right, but when you show at the end the distribution of the different populations within the galaxy, and you say that for the young stars, it does not quite well. I can imagine that it's because they are all distributed like at the outskirts of the galaxy instead going to the center. But then what is your conclusion about the intermediate age stars? Because doing planetary nebulae, I'm very much interested in this. They should be in whatever place in the galaxy, kind of distributed, I don't know, homogeneously, perhaps in this intermediate population.
The intermediary is good. Just the young population that we have this problem because the spectrum is like a plan. Then the way that the all-star makes the fitting is get the young population with dust. Then the problem is just with these areas here.
So the problem is to
intermediary.
deal with dust versus the young population only. For the rest,
Yes.
Okay, thanks.
Okay, we have time for one more question, a
We
little
have
one.
we have one here, Eduardo Teles.
Yes, go ahead.
Hi, Julia. Very good work. My question is, you notice the features in your tomograms, but these tomograms that you found the features are very high numbered tomograms. That means that they're very low variances. In tomogram 7, 8, 9 that your features popped up. My question is, in the tomograms that have higher variances, that are lower numbers, 2, 3, 4, you do not see any particular features, or did you ignore them, or what happened in the ones that have higher variances?
You here. The first have the mark variance. That's it.
Yeah.
Yeah, they have more variance, but here we can't see make the interpretation. Then we can just sum like this one. I don't know. I don't know make this interpretation.
Okay.
Or is that?
Okay.
No.
Well, thank you, Julia, again.